So yesterday we have worked out this problem, and we have another problem. There are several problems in the book. Say, if you look at this problem, this is somewhat similar to what we have done yesterday. So if you look at this, the trusses are pin connected and suspended from the parabolic cable. Determine the maximum force in the cable when the structure is subjected to the loading shown. So these are the two loadings. So don't worry about these units. You can still try this one. Like we did yesterday, we have to develop a equation for the parabolic curve from dy by dx is equal to tan theta. Then from that, similar to what we did yesterday, we can find the angle here. So and uh, from that point onwards, we can start finding the forces. So similar to what we did yesterday, so you don't need to worry about what is the structure below and what's the loading here. What we are interested is the load acting on this cable. So what we assume is the load is uniformly distributed on this cable so that we can find these forces later. So similar, following the same steps we did yesterday, we can do this one. So try it by yourself. Now I'm going to a new section in cables and arches, that is analyzing arches. So arches, like cables, arches can be used to reduce the bending moment in long span structures. Essentially, an arch acts as an inverted cable, so it receives its load mainly in compression. Although, because of its rigidity, it must also resist some bending and shear depending upon how it is loaded and shaped. So we know that the cable is shaped like that and it carries force by tension. Arch is going to be a shape like this and it is going to carry the force by compression. The arches, if you look at it, goes back to very long time. Okay, so the origin of arches, how it has started. So this is a temple in Malta that is 3600 BC. Just look at the age. It is about 5600 years ago from now. So they have tried to build something. This is the very primitive starting point of arches. So people had an interest to, have some sort of opening like this, or like a temple like this. So they can they can keep something to worship. Oh, here like Stone Age, this is supposed to be a burial place. And here also people try to like create an opening, a door, okay, a door, and to the entrance to something. So this is how it started. Now, when you have this opening to be wider and wider and wider, so you can't have this sort of a stone. You can't look for this sort of a stone or this sort of a stone as always. And as the span increases, the stone may become brittle and fail. So in such a situation, so this is another type of arch, early primitive arch that is in Ireland. So then what happens is then they started building like this. Say you can see as kind of a trying to formulate an arch like this. And then this came this cobble arch sort of thing. Now here, instead of a one single stone, they started doing brickwork. So the brickwork, and then there's an opening, and this is 1250 years ago before Christ. So it's about 3250 years now. So then the Persians have mastered this art of an arch. So from the Persia, it moved to Europe. So here you can see an arch, a perfect arch is constructed in a temple in Iraq in 2100 BC. So this could have been a little bit later. And then the Romans have extensively used these arches for various structures. So one of the main reason they were started using these arches in aqueducts, because when Rome was flourishing, they needed to bring water from faraway places. So aqueduct is a structure they brought water from faraway places or somewhere to fulfill the need of the Rome's water requirement. So this is in the around 40 to 50 AD. So that means about 2000 years ago, this aqueduct was built. So then, now you can see a massive span can be achieved using the brickwork in the form of an arch. So here the span is small. The Romans have mastered the art, and then they made it their arch, wider and wider. So they might be able to construct very sophisticated structure. So if you look at arches, there are they are in a parabolic shape, and it is subjected to a uniform horizontally distributed vertical load. Then from the analysis of cables, it follows that only compressive forces will be resisted by arches. So similar to the cables, we assumed only tension. Here we assume only compression. So this is a fixed arch. So it is fixed at both ends. This is a two-hinged arch. There are two hinges here. And there's a three-hinge arch. So here there's a hinge, there's a hinge here, there's a hinge. And this is a tied arch. You have an arch, two hinges, and it's tied. So now when it comes to analyzing an arch problem, okay, most of the problem that we encounter tend to be a three-hinged arch. So whatever the problem that we come across in this subject is three-hinged arch. Now let us see. If you take these forces, determine the resultant forces at pins A, B, C of the three-hinged arch roof truss. So here there's a hinge, here there's a hinge, here there's a hinge. Okay. So you are asked to find the resultant forces at the pin A, B, and C. So you can do it when it comes to a problem like that, you can do it in a simple way. You can take one part of the arch and then you can mark the forces. Okay, when there's a hinge there, you have only two reactions. And you can find the reactions by taking equilibrium of the arch. Okay. So I'll come back to this. And then here there's another type of arch. So some of the bridges are constructed like that. So, and this is a tied arch. This is fixed at two ends. a 3-hinged arch. So let us go to the book. Cables and arches. So the 3-hinged arch, you can see like it is analyzed like this. Okay. It's analyzed like a simple structure. You have you can break at the hinge and you can mark the support reactions and you can find the support reaction. And if you cut somewhere else, then you in the similar to a beam, you can mark the forces, axial force, shear force, and then moment. So if you look at the analysis steps, so similar to what we have done, say you take the entire arch and then you can find the uh, reactions, okay, and then you can find the internal moments as well. Okay, so this is relatively a simple. These are the solutions we are looking at. So let us go back to our solution. First one, problem. And arches. So if you take this one, so here you can mark these reactions RA, HA, here RB, HB. So if you balance vertically for the entire structure, RA plus RB minus 2 minus 3 minus 4 minus 4 minus 5. So it's 9 and 4, 13, 13 and 5, 18. 0. So this is first equation. And if you take moment by A, so then J and RA will cancel off and then HB will cancel off. So we can find RB. So RB into the distance is 3 plus 1, 4, 5, 5 plus 3, 8, 10, 10 plus 3, 13, 15. RB into 15 minus 2 into 3 minus 3 into 4 minus 4 into 5. So these are distances from A. So 3 meter, 4 meter, 5 meter, 8, 10 meter minus 4 into 10 minus 5 into 30 is 0. So 15 RB minus this is 6 minus 12 minus 20 minus 40 minus 65 is 0. So 15 RB is equal to 65 plus 40, 105, 105 plus 20, 125. 125, 12, 135, 37, and plus 6, 143. So RB is 143 divided by 143 divided by 15. That is 9.53. So RA is 18 minus 9.53. So that is 8.47. Okay, so those are the RA and RB. Now let us break this structure into two components. So if you break this at the hinges, so here I will have, should be RC and HC, but it's okay. Let me mark this one as R1 and H1. This one as RA, HA. So RA is known already, 8.47. And here we have three forces. 2, 3, 4. So if I take this equilibrium of the section of the arch, section, so we have to consider equilibrium RA plus R1 minus 4 plus 3, 7 plus 2, 9, 0. So RA is known 8.47 plus R1 minus 9. 0. So R1 is 9 minus 8.47. So that is 0.53 kilonewton. Okay, 0.53 kilonewton. Then if you know the R1, the H1 we can find by taking moment at A. Okay, taking moment at A, you can find R1 into the distance is 3, 4, 5, 5 plus 3, 3, 4, 5, 5 plus 3, 8. 8. R1 into 8 plus H1 into the distance is 5 meter. So this distance is 5 meter. It is given in the H1 5 minus 2 into 3 minus 3 into 4 minus 4 into 5 is 0. So R1 is 0.53. So 5H1 is equal to 3 into 2, 6. 3 into 4, 12. So 6 plus 12, 18. 18 plus 20. So 38. So 18 plus 38. So 38 minus 8 into 0.53. So 8 into 0.53. That is 4.24. So 38 minus 4.24, 33.76 divided by 5, 6.752. Okay, so H1 is 6.752. If you know H1, you can find HA. HA is equal to H1 because it will balance proportionally. So HA also same as H1. 6.752. H1. So if it is HA is 6.752, HB also 6.752. because you take the entire structure, if you balance horizontally, HA is equal to HB. So this is how you can work out this truss problem. Sorry, the arch problem. Let us take the second example. Now we know the reactions, right? We know RA, we know RB, we know RHA, we know R1, H1, we know RB, HP. I mean, I have taken this as RB and HP, but it is supposed to be RC and S. Okay, so you have to look at it. Now we have a 3-hinged spandrel arch is subjected to the loading shown. Determine the internal moment in the arch at point D. So we need to look at the moment at this point D. Okay. Let us see how to do this. So these are the problems in this book, right? So I have taken some of those problems. So that's all we need to look at. This chapter gives you a very simple understanding of analysis of arches. It does not mean that you can even analyze much complex arches, but yes, you can have the basic understanding how the arches are analyzed. Okay. So example 2. So here we need to get the moment at D. So like the trusses, we need to look at arches as a separate element. Okay. We need to look at arches. So to get that D, we need to cut it like this. Okay, we need to cut it like this, and then we need to get that internal forces and moments. But before that, we need to find these external forces. So here you have a 3-hinged arch. So this is a hinge, this is a hinge, B is a hinge. So hinge means you have this forces. Okay. RA, RC. Then there will be a horizontal perpendicular to this one. That will be HA, HC. Okay, so these are the forces. So you can mark it like that, or if you want, you can mark vertical and horizontal as well. No harm. So you can mark it as a RA, RC, and then HC, and H. Since it's a hinge, we can mark in any way we like, because we are considering only the from here to here. We don't care how it is connected to the support. We are interested in the hinge. So if you take vertically, okay, so RA plus RC minus the forces are 4 plus 8 plus 8 plus 4. That is 16, 24. Here 12 plus 6, 18. So 24 minus 18 is 0. So RA plus RC is 42. Okay. Then if I take moment at A, then HA and RA will cancel off and HC also will cancel off. So RC into 16 minus 4 is acting through this point. So 4 will not be considered. So 8 into 2 minus 8 into 4 minus 4 into 6. Okay, and minus 3 into, so the distance here is total is 16. Here 6 gone means it's 10. 3 into 10 minus 6 into 12 minus another 6 into 14 minus 3 into 16 is 0. So 16 RC is equal to the sum of this, that is 8 into 2, 16 plus 8 into 4, 32 plus 6 into 4, 24 plus 3 into 10, 30 plus 12 into 6, 72 plus 14 into 6, 84 plus 16 into 3, 48. So that is 306. So RC is 306 divided by 16, 19.125. So if RC is 19.125, then RA is 24, 34, 42. 42 minus 19.125. So that is 125, 22.875. Okay, 22.875. So these are the two values, RA and RC. Now, if I cut it here, okay, I can find the RB and HB as well. So once I find RB and HB, I can find HA. So that for that, in order to find HA, I need to cut it here and take a moment here. I can take a moment from point B. So if I cut it like that, so there is a HB, RB. So here RA is known, that is 22.875, and HA is unknown, and there are these forces. Okay, so the forces are acting through these lines. Now, if I take moment by B, I can cancel off HA, HB, and RB, which is not necessary for me at the moment. So I can find HA. So if I take moment by B, HA into the distance is 5 meters plus 4 into the distance 8 plus 8 into the distance is 6 plus 8 into the distance is 4 plus 4 into distance is 2 is 0. So 5HA is equal to 32 plus 24. So 32 plus 48, 32 plus 8, 120. So that's divided by 5, it's 24. So 5HA is 120, so HA is 24 kilonewton. HA is 24. So once we know HA and RA, Now I can cut it here. Cut it at that point. Yeah, we are interested to find the internal reactions at D. So we are internal moment in the arch at point D. So if I cut at that point at D, so here I have the reactions known. It's on 524, and I have this force. The 4 is acting here. Then I have this force. That is 8 is acting there. So I'm cutting this at this point. So when you since these 4, 8, and everything is acting through this line, when you cut it like this, there won't be any forces in these points because there is no force. I mean, that these are spanning between these two supports, and there is no force because there's no load acting in this point. Okay, because all the forces are transferred through these studs. So I can mark this. To take the point D, there will be an axial force HB. There will be a shear force SD, and there will be a moment MD. So at D, if you take a moment, SD and HD will cancel off. So MD, that is a moment at point D. Then that is counterclockwise. Then 24 into 24. The reaction 24 at 3 meters, so that is counterclockwise. So that is going to rotate like this. So 24 into 3. Then these forces are going to cause clockwise rotations. Counterclockwise. That is 4 into the distance. From this point, the 4 is at 3 meters. 8 is at 1 meter. Okay. So 4 at 3 meters plus 8 at 1 meter. Okay. Minus 22.875 into the distance to 22.875 is 3 meters, is 0. So MD, so that is 22.875 into 3 minus 24 into 3 minus 4 into 3 minus 8 into 1. So that is 23.375. So MD is minus 22.875. So 23.375. 23.375 kilonewton. So that is the moment at point D. Okay. And you can balance horizontally, vertically, and find SD and HD as well. Okay, so that's also possible. So that is how we can work out this. So if you look at this one, I'm not going to do this, but I'm going to tell you. Reactions at A and C. Here you have to, if you take the entire structure, you don't need to consider the force acting in the tie this tie we don't need to consider. If you consider the entire structure, so you can mark RA and HA and here RC, then find the reactions like a beam. You take the equilibrium vertically, horizontally, and find it. Okay, and then determine the components of reaction at AC and the tension in the cable. So once you found the support reaction at AC, B is a hinge, so you can cut this, and you can cut this as well. So then you can find the support reaction. So if you take this one, horizontal and vertical components of reactions at A, B, and C of the 3-hinge starch. A, B, C are pin connected. A is pin, B is pin, C is pin. So again, the same way, you have to mark the support reactions. And here it's a bit tricky bit because the reason is you have the location at 2 different locations. Okay, so you can try this one and see whether you can approach this problem. Okay, so I will work out this and post this as a worked solution, so you can see whether your results are same as this one. So this is how we analyze the arches. So basically, cables and arches, it gives us a bit of a flavor of a basic understanding of how to approach a cable or arch, because cables and arches are used in bridges. They are used in like in buildings. So there is a wide application. So this is a very important subject, and it's very interesting subject. So I hope you have gained some knowledge on how to analyze cables and arches. Next week, we are going to start influence lines, and there will be a quiz on Monday from cables and arches. Okay, so there will be a quiz on Monday from cables and arches, and we will have a new section next week starting Thursday, influence lines. So let us stop here, and I will work out the solution and post it for your reference. You can look at it. And if you have any questions in the meantime, you can email me or you can WhatsApp me, and I'm happy to help you with any solution or any problem. Okay, thank you for joining in the morning. I'll see you again on next Thursday morning. Monday, there will be a quiz. Please note that Monday, there will be a quiz on this section. Thank you.